So our next speaker retired and started to enjoy his retirement phase 6 years ago. Great to still have him here. As said, Steve retired in 2018. He retired after being 39 years with Pfizer, and almost 30 years out of this time he was senior director and team leader for Process Analytical Science Group, PESG, and also responsible for global technology organization. The last 10 years of Steve's time at Pfizer, he had heavy focus on development of analytical and solutions and control systems, PCMM, continuous manufacturing, all this stuff. As said, he's enjoying his retirement, and as such, he is now an independent consultant working in the area of analytical science related to manufacturing of pharmaceutical and food products, and he's working with Phil Doherty as Acuitas. Great to still have you here, Phil.
Thank you.
It's your audience.
Okay, so what I want to talk about are these fiber optic probes, because as we in Pfizer started to want to move towards continuous manufacturing, obviously the measurement systems are very important, and we started to have a lot of focus on these fiber optic probe sampling systems, because on face value they look absolutely perfect. You just poke this probe into your process and away you go. You get all this information about what's happening in real time in a process. But it isn't as simple as that. These probes they're wonderful things, but they're not Harry Potter's magic wand. And they need to be used very carefully and to understand in each particular case that it is product dependent and process dependent on how well these probes might work. And you need to almost empirically understand how a probe is going to work in a certain process. And what we needed to do, because these things are going to be in-process equipment, was to find a way of researching and understanding how they would behave in a particular process, but not use the processing equipment to do it, but to find a way of simulating that environment. And here is the first version of these things for simulating the environment of a fiber optic probe. And it's actually amazing, because the first time we used that antique, that's the Model T Ford of simulators, the shiny one you saw next door a couple of days ago is about the 5th generation. This is the original one. So this is the Model T Ford. This is in Dresden. The first time we actually used that, we brought it here because we needed to understand why the Sentronics instruments were never the same, because every one that we bought was slightly different. And that was going to give us a problem, because we wanted to use these as twins, not digital twins, but just physical twins that are in pairs. So if the fiber optic system broke down, we could just swap it out with another one. So that system was brought to Dresden to do exactly that. And we worked with 2 young researchers that you can see here with the 6 instruments that Pfizer actually was buying from them, to find out why their instruments weren't all the same. So there they are. And a whole team of people, including Phil and myself and another bunch of people around the table, working for over a week on why those instruments weren't the same. And in the end, we actually did some very useful work, and actually Uwe talked about this yesterday, because at the start of that week, you could see the left-hand plot shows you how different the instruments were. But by the time we got to the end of the week, Uwe and Sebastian had figured out what their problem was, and they fixed it very, very quickly. And it was just as simple as improving the calibration system for the spectrometers, which Uwe talked about. So our focus inside Pfizer, and you've heard so many descriptions of this, but this was the ultimate thing we wanted to do, was to put the probes into the feeder of the tablet press and use that measurement of the powder just before it became a tablet to substitute from sampling tablet cores and analysing them. So this was their focus, was to put these probes into a feed frame. Now, why the feed frame? If you think about a diffuse reflectance probe, that environment inside the feed frame is just about heaven for a fiber optic probe using diffuse reflectance, because that feeder system is designed to keep a powder at a very constant density, very constant dilation, and it's moving it at a very constant speed. Now those two factors mean in that environment, a Sentronic's FO probe will work as good as it's going to anywhere. But there are still some things about using it in that environment that need to be considered. And that's what I want to talk to you about, is the complexities of what you might have to do and cope with putting a probe into that environment. And this is the simulator that we were demonstrating early in the week. And you can see that it's purely a case of putting about 100 grams of powder into this rotating device that it does simulate, in fact, half of a Courtois feed frame that goes into the press. So the powder is circulating in that, and on the tablet press, it's being pushed down into the dies of the tablet press. And that powder, within a few centimeters of being circulated, and there becomes a tablet. Phil talked about this earlier, but the one thing he didn't tell you, that this is 2 batches of the same product. And you can see that one of them is very, very uniform, and the other one is not. And they both pass specification. And it is just a factor to do with the batch of raw materials that was used, particularly the API. So they both pass specification, but spectroscopically they're going to give you quite a different answer. And that's one of the complexities of using these fiber optic probes, is that you do have to cope with the matrix not always being completely the same. And for those of you who don't know what this is a near-infrared imaging system where 10 micron squares, a spectrum has been taken of every 10 micron squares, and the material that's actually in that square identified chemically from its spectrum. So this is, if you like, a chemical picture of the matrix of actually a blend in this case. And this is not unusual. This structure, this microstructure of blends, is very, very common. In fact, it's actually rare to get a really well-mixed material that you see on the right-hand side. It's more likely you're going to get the material on the left. And the main reason for that is that it seems in pharmaceutical manufacturing processes, like materials often coalesce together, particularly the API, which tends to be very cohesive. It will form these clumps. So that matters when you're trying to use a fiber optic probe. And one of the reasons for that is the amount of material that actually contributes to a spectrum if the blend is stationary in front of the window of the probe. And there's some description of how this is calculated. It's the depth of penetration, the density of the powder. All of those things contribute to how much material actually contributes to a scan when you take the probe. And the bigger area you scan, the more sample you actually you examine. And that's why the BU unit has a big window. Well, because these fiber optic probes have got a fairly small window, about 5 millimeters across, the amount of material that actually contributes to a spectrum, if the powder is stationary in front of the probe, is only about 3 to 5 milligrams. And there's a real big problem with that. One is that non-homogeneity of the blends you're looking at, and the fact that we need to do measurements at a unit dose weight. And 3 milligrams is not a unit dose weight. There is no product that's sold with a weight of 3 milligrams. They're usually 300 milligrams. So that's one of the limitations of those fiber optic probes. They're very convenient, but they only see a tiny amount of powder. Now, the way we get around that, I'll come to in a minute, but just some evidence that this is a real big problem. Here, myself and Owen actually did this work. We scanned powder, a blended powder, on a dish where we were just covering the fiber optic probe. So we would put the powder there, we would scan it, And then we would move it with a stick and agitate it and scan it again. And each of these blends, there were 7 of them, we would scan them 10 times, but agitating the powder between them. But every time the powder was stationary while it was scanned, and then try to make a calibration using that data, and you can see how bad that is. And that is all to do with the fact that you're only collecting a spectrum from 3 milligrams of powder, and it isn't representative in terms of a unit dose weight. Now on the right-hand side, we've actually put the powder into the simulator, and we're moving it and scanning it as it's moving. So essentially, what we're doing in that case is doing this. We're scanning our 3 milligrams, but we're moving the powder fast enough that every time it scans, new powder has been moved in front of the fiber optic probe. Now, actually, in fact, this turns out to be useful. It was a problem, but with continuous processes, the materials are moving. So, you know, a continuous process is actually allowing us to get round that problem because it is moving the powder, and we can scan repeatedly, integrate a number of scans and get a unit dose weight. In this case, we've taken 50 scans of the moving powder at 3 milligrams each, so our sampling is 150 milligrams, which is, you know, getting towards a unit dose weight. Now the question is, for any particular product, how many of these scans do I have to take? If I've got a 500 milligram tablet, how many scans do I have to take to get a representative sample? Now, it may not be that you need, an actual fact, for a 500 milligram tablet, you might not need to take 150 scans, but there is a way of empirically finding out, and this is how we do this. What we did was to take 1,000 scans of the powder as it's being moved, and then take those 1,000 scans and put them into groups. For example, in this case, there are 10 scans there, but we actually went from 1 to 100 scans. So we would take a group of those scans, say 10, we'd get the average of those 10 scans and say, well, that's a spectrum, and we would actually create 20 spectra using groups of 10. And we'd vary the group size from 1 to 100. So in that way, we can look at how, if we take different numbers of scans and make them, average them into a spectrum, how many scans do we need to do to get a stable spectrum? Well, here's the curve, and you can see as we increase the number of scans, the spectrum that we're collecting with the probe stabilizes, and we know that we're going to get a stable representative spectrum. And I think it's very important that people understand that you do need to do this for every product. In fact, this curve relates to one wavelength, and that's the wavelength of that particular API. In fact, it's saccharin. So an empirical way to use the simulator to determine when you're going to get stable representative sampling in that type of feed frame environment. One of the other things about those fiber optic probes, they do suffer an effect from pulsing, particularly things like some feeders, but mainly mixers. The tubular mixers cause pulsing. And when you think about how fast that probe is actually collecting its data, it can be just half a second to get 50 or 60 scans. So it's very, very fast. And if that starts to get in phase with the pulsing of a mixer, you can get some effects from the fact that the pulsing is causing an acceleration and a slowing of the powder. And why does that matter? It's because if you start to change the velocity of the powder, and that probe is scanning at a constant rate, if the velocity of the powder changes, the size of your representative sample changes. So that's one of the things about those types of probes. In the feed frame of a tablet press, it's okay, but if you put that probe into any environment where the velocity is not constant, it will start to give you errors. So you can't really use these fiber optic probes in an environment where velocity is not constant. And the worst one of those is these gravity-fed chutes like this. And you can see in here, if you look at every now and again there's a flash of light, and that's because the flow of the powder is dips enough that the light gets through. So those sorts of chutes are a very poor environment to put a Sentronic FO probe. And unfortunately, a number of companies that sell continuous manufacturing equipment have a prevalence for selling these chutes. In fact, some spectrometer companies have been known to do that as well. Not mentioning any names, but the effect of that, and this is some data given to me by Anders Sparren from AstraZeneca, who just retired. The performance of calibration over here, you can see there are 3 levels of API. And certainly the near-infrared is getting the relative concentrations right, but look at that horrible noisy baseline. And that, again, is effect of pulsing in these gravity-fed chutes. Now, the solution for that type of problem, just as a warning, my recommendation is you do not use those chutes. So if you look at the sample size that we're taking, it is actually, if you stretch it out, it is a curved oblong, if you like. And here, actually, Phil did some calculations on the contributing weight and how long you're scanning and how fast the paddle is moving. So this is all specific to the speed of rotation of the paddle wheel in the feed frame and how long you're scanning for. And you can use this to sort of estimate sample size against how long you scan, against how long the powder is moving. So this is just an estimation, but the best thing to do is to empirically measure it and know that you're setting the fiber optic probe up to be successful. In fact, this is some other work that I think Uwe and Phil did this, looking at what happens if you change the speed of rotation of the paddle wheel. And if you look, it starts off at 10 RPM, and if I flick through these quickly, you'll see as they change the speed, the prediction error decreases. But as you get further along, in fact, you start to get to 50 RPM and it increases. So again, here's an indication that you need to empirically measure what the optimum rotation rate is to get the minimum error in a calibration. I want to come back to, here's a curve of those speed of rotation against the error in the calibration performance. I want to come back to this problem of a chute, and there's some really good work that was done by a mixture of Rutgers and Mayagüez University in Puerto Rico, where they looked at the performance of a near-infrared in a chute, a free-fall chute, the one I just told you not to use, against measuring in the feed frame of this tablet press, as against taking tablet cores and measuring them in transmission in a lab. So there's 3 different positions: the free-fall chute, the feed frame of the tablet press, and then putting the tablet cores into actually a Brooker MPA in a lab, and looking at the performance of the measurement in terms of how much error you get. So this is the free-fall chute, and you can see these wide scattered bands are telling you the prediction errors are quite large. You put it at do the same measurement in the feed frame, and you can see the way the error bars have narrowed down and are almost the same as doing the transmission measurement in a laboratory. And as this is not a Sentronic user group, I can mention the fact this was done with the Viavi. So, but I think it really illustrates the data, shows you the dangers of free-fall chutes. And some more information which I found very interesting, that as you change the speed of the mixer, it was a tubular mixer, and again you got some difference in performance, but not with the feed frame or obviously the offline tablet transmission. But certainly the free-fall chute is very sensitive to the speed of the mixer. So in Pfizer, we did need in places to do measurements in chutes. And the way we got around that problem of the effect of serendipity in terms of the flow because of just relying on gravity was to put this device here, this spider wheel, into the chutes, or actually into tubes. And Expo have been making these for Pfizer for quite a while, different sizes. And you can see this is a way of taking a flowing material that's coming down a chute and capturing it with a spider wheel and making sure that the powder moves in a consistent density and a consistent velocity. So this is a way of overcoming the problem of free-fall chutes where you can get a difference in velocity of the powder, which causes errors in the prediction of the near-infrared. And one of the great things about this device, and Phil and I found this out recently, that we wanted to look at transferring a calibration from a feed frame into this mechanical device. And you go to all the lengths of figuring out how to do that transfer. But in the end, it was actually easiest just to get a flower pot, cut the top off it, and put a shell around the spider wheel, in which case it only takes probably 100 grams, and you could actually scan everything in the spider wheel and develop a calibration without actually going to all the complexities of mathematically transferring them. Just use a flower pot and collect the data in the spider wheel. But if you look at the idea of transferring them, you're using the same sort of fiber optic, and this is, I've tried to do the shell of the feed frame simulator here. The probe is in this environment with the spider wheel. It actually has the spider wheel fingers have got a PTFE backing on them that wipe the probe over. So there is a difference in how the data is collected. But what we did find is that if we looked at the difference in collection parameters, like the speed at which the velocity of the powder, if you actually corrected for the different sizes in the wheels and corrected for the velocity of the powder, got the velocity the same, and then overcame the problem of outlier rejection because the fingers of the spider wheel itself and the one that's not in the feed frame, there is some rejection of outlier spectra that Owen talked about earlier. And if you compensated for that and the velocity of the powder, you could actually transfer calibrations from the feed frame to the spider wheel. But this plot here is actually not transferring it, but this is the spider wheel with a flower pot on the left and the feed frame on the right, and the calibration performance is exactly the same with the same samples. So, conclusions: it's important to investigate probe-based methods in a dynamic environment that does simulate the actual environment the probe is going to be in, and you have to do that with every specific product you're going to work on. You know, different products with different ingredients, you've got to investigate them individually because they may have characteristics that are just a little different. I mean, you can start in the same ballpark, but you do need to be careful about whether a probe is going to be absolutely optimized for each product. And the number of things that you've got to understand are the speed of rotation of the spider wheel, how fast we're scanning, how many coads we're taking. All of those things need to be really studied and optimized. The one thing about this system is, though, that even with the offline spider wheel, you can still characterize that with probably as little as 50 grams. But in terms of the putting material into the simulator, that simulator needs only 100 grams of material, and you can gather just about all the information you need to know about how well a fiber optic is going to perform with that particular formulation. And with that, I thank you for your attention. Just one other thing. This is a reference to a paper that talks about using that simulator to develop calibrations that actually worked on multiple tablet presses. I think it's an excellent reference in how to use the simulator and a fiber optic to get very good results.
Thank you, Steve. Great talk. Once more. Hope we will be able to add a few more in the future. So, questions to Steve? Bent.
So when we saw your feed frame simulator yesterday, you had a cutout of the spider wheel to where the probe sits. So is that just to not hit the probe, or is that to prevent outliers?
It's to prevent outliers. I'm a firm believer if you can engineer out any disturbance in the spectroscopy, basically using engineering solutions rather than chemometrics, that's what I do. So that notch means that there is always at least a millimetre of powder between the metal surface of the finger and the probe tip, because if diffuse reflectance probes shine light down onto a bare metal, you get a big bolt of light coming straight back in there, and it adds noise to the spectra. So it's better to engineer out that effect and try to remove it by chemometrics. But the outlier rejection system in the Sentronic software will do that.
Exactly. And it's not chemometrics. Isn't there a paper from Elizabeth on this pedal finger wheel design?
Yeah, we published with the University of Ghent, Elizabeth Peters, Professor Thomas de Beer. They did a lot of work looking at the size and shape of the notches and how to optimize those for using the fiber optics. I think the other thing I need to mention is that Owen has done some work with Rutgers, and they're hopefully soon going to produce another paper that will talk about these dreadful gravity-fed shoots. But I'm waiting for that to be released.
Steve, I also have a question. After playing with the feed frame simulator a bit the last days, the notches, are they also helping with the mixing efficiency in the system, and how much are they affecting the mixing inside the feed frame simulator? If there would be notches and no notches, I had the impression that the mixing would also be quite different depending on how you make that notches, for example, how deep and wide and everything.
Yeah, it's a good point, Uwe. I mean, the one thing that we were worried about, or at least Courtois were worried when we said we were going to cut notches into the fingers. They said, well, we need to understand what effect that will have on that feeder system. So they did some calculations, and they said, in actual fact, it would make 4% difference in the pushing efficiency of the powder being pushed into the dies. But the effect on mixing, I don't know, but I think intuitively, I think you're right. It probably does help to move powder between the finger, the cells that you have between two fingers. Powder does move between the cells, so it could help with mixing.
Okay. Oh, more questions.
Maybe we could get rid of the notches if only the spectrometer could be triggered one day.
I think that's relatively easy to do. Put an encoder on the axle of the, and actually only fire the spectrometer when the finger isn't there. In fact, I think someone's already done that.
But so far, I have heard by Sebastian, the spectrometer does not accept trigger signals.
That's not correct. It depends on which spectrometer or system type we are talking about.
Well, if you use the Sentronic software, there's a lot of things you can't do. But if you use someone else's software, there are lots of things you can do.
No, thanks, Steve. We know there's a lot to do in the software. No questions. But that was not what I wanted to say. What I wanted to say is that I think the outlier rejection really does a great job on eliminating most of that variance, if with notches or without notches. I wouldn't be afraid of running our systems without that notches and challenge that methods without doing triggering, because I think the outlier can really do that.
Yeah.
And if software-wise necessary, we could use the physical changes in the signal to actually create kind of a trigger, just based on the data. But I'm not even sure if this is necessary. I doubt this at the moment.
No, I do agree. I think the outlier rejection it's a godsend. I don't know what we would do without that, because if you start to collect lots of data that's an outlier, and you get disturbance in the spectra, then in theory you've got to explain that to a regulator. And I think a filter system that's genuinely validated and what it's doing is worth its weight in gold.
Okay, Clement, last question.
Yes. In your video with the feed frame, I noticed that you didn't feed it up all the way to the brim, so you had some gap with the fingers. I was wondering, are you not afraid that there is air pocket in front of the probe? And why would you leave a little bit of air inside? Is it for the mixing of the powder?
Well, in terms of the filling up, I think the problem was there that we just didn't run the video for long enough. But in sometimes it depends what the product is, but you may get air pockets. And again, I think what you've got to be very careful of is the level sensor in the feed frame, is to make sure that that is adjusting up far enough that the probe is always going to be down in the powder bed. So that's a case of designing the notches that the probe can go down far enough, as well as the level control in the feed frame. Well, for the simulator, I mean, we can just look through the window and see that it's full. But
there have been a few fingers more. We were talking about fingers of the spider wheel, but let's now go ahead with our break. There's cake outside. I was checking it. It tastes well. It's there. So we will either see again here 15:15 or 15:16. I'm going to chase you in. So see you then.